And we're back. Okay. Try to think of a pattern. What would you do to each string? Each string, what would you do? Does someone want to tell me in English, not Python, what would you do to each string? Replace what? Space with underscore. And then what? Take everything but the last 5 characters. That sounds good to me. So see if you can, if you didn't get it before, in the next 60 seconds. For each string in this list, replace all spaces with underscores and take everything but the last 5 characters, which are space, parentheses, CM, parentheses. Replace spaces with underscores and take everything but the last 5 characters. So for each species dot replace space with underscore. If I just do that, features is now with an underscore, okay? And then I'm going to take everything but the last 5 characters. That's it. By the way, there's another file called O5 Iris Query Solutions that has all of the answers already filled in as well. But if you're trying to challenge yourself, please don't look at that file. But that it does exist. So later on, when you look back, the solutions are all there. So now I have these features. And again, we like this because the centimeters, we know it's fine, we get it. And we don't want spaces because in case we need to use the dot notation, we want to use a dot notation, we have a one-word column name. Fine. So now, line 35, we can read in, create a data frame using iris.data. Does anyone remember what iris.data is, just by itself? What type of object is iris.data? You remember from above? That's the ND array. That's this giant thing on the right. It's a 2-dimensional array with 150 rows and 4 columns. I'm going to create a data frame of it, bless you. The data frame instantly recognizes the rows and columns. And then I'm going to give it an optional argument, columns equals features, the pretty list we just made. So when I do this and then look at df, now it's a column. Or it's a data frame. It's a data frame with column names above and the index. This is the normal data frame that we're used to now. So now we've gone from NumPy to pandas. Okay, so far all we've done is make a data frame. Fair enough. The next thing we're going to do is we're going to make a species list. Species. Now, we already have iris.target, with a bunch of 1s, 0s, and 2s, right? And what are each one? Well, if you look at iris.target names, 0 index Setosa, 1 index versicolor, 2 index Virginica. So anything with a 0 is a Setosa, with a 1 is a versicolor, or with a 2 is a Virginica. What I want instead is a list of species that instead of saying zeros, ones, and twos, it's setosas, versicolors, virginicas. So species should end up being a list of 150 strings, which is either setosa, virginica, or versicolor. So you see this iris.target with the zeros, ones, and twos. Essentially, species is this list, but wherever there's a zero, it's a setosa. Wherever it's a 1, it instead says versicolor. And wherever it says 2, it instead says virginica. So take the next 2 to 3 minutes, talk to your partner, and see if you can create a list of 150 strings, setosas, versicolors, virginicas. The first 50 should be setosa. The second 50 should be versicolor. The last 50 should be virginica. You can do it however you want. I give you a hint to use these two arrays in a list comprehension, but you can do it any way you want. You can write out 50 setosas for all I care. Here, you have 2 minutes to do it. And I'm not doing this to be like, you have to do this in 2 minutes or else you're not going to be able to understand the rest of the lecture. The purpose of the time constraint is to get your brain thinking. In the non-pressure environment of the classroom, I'll shut up now. Here's another hint. How do we know what zeros, ones, and twos are? They happen to be the index of iris target names. So for 0, if you ask me what is a 0, it's actually iris target names 0. Is setosa. What is a 1? Iris target names 1, versicolor. What is 2? Iris target names 2, virginica. So how can you combine those two arrays? One simple list comprehension to create that list. Zeros should be setosas. So, for each flower, so for flower in iris.target, so here's how I write a basic list comprehension. I write the basic one, flower for flower in iris.target. So all that is the exact same list, zeros, ones, and twos. But instead of flower, which is either 0, 1, or 2, I'm going to do iris.target names flower. So using the index of iris target names, now I have a list of setosas, versicolors, and virginicas. That one was tricky. So we actually happened to notice that the zeros and ones and twos were correlated to the index of iris target names, and we used that fact to quickly make a species list. So now that we have, by the way, if you want to just quickly catch up, you can go to the iris pre-work solutions and just copy and paste the solution. It's the same exact thing with the different index that I used. You can just copy and paste it into the in here, or just follow along in the solutions if you don't want to do this. But I suggest you keep doing these problems with me, along with me. So species is now a list of strings. I'll create a new column in my data frame, df species equals species. And now df has 5 columns. If you were wondering why we're doing this, well, if you remember the first time we ever loaded iris CSV, I made that CSV by doing this. I took it from scikit-learn and I changed the column names to be something nicer and I added them into a data frame and then I did .toCSV and then put that on GitHub. So you're watching me create the exact CSV that I let you use last time. This is how I did it. So we can do our basic data frame work, right? We can dot describe. We can do group by species and then get the mean of the sepal lengths. We can group by species and get the mean of the 4 categories. And the whole point of doing this is our human learning. We're trying to find differences between the flowers. Now, looking at petal length, can someone tell me something interesting about petal length in terms of differentiating between species? Yes? Setosas have very small petal lengths as opposed to versicolors and virginicas. It almost seems like it's a pretty safe bet, probably. If I say petal length is less than 2, it's probably a setosa. Off the bat, it kind of seems that way, but let's keep going. What about petal width? Anything? Also similar. Setosas have very small petal widths. And also the difference between petal lengths, petal widths, between versicolors and virginicas is also kind of distinguished. As you can see, in sepal width, 2.7 versus 2.9 are very close together. However, here in petal length, the average is 1.3 centimeters between the versicolor and the virginica. It almost seems as though petal length and petal width by themselves do a good job of separating out the species. Let's keep going. Ag is a new function that we're seeing right now. Ag stands for aggregate. Why we did NumPy today is this is one of the reasons. Well, we can do df.groupBySpecies.mean. Ag is a function where you can give it your own function and it will take each of the columns and then apply that function to the column. So here, we're going to group by species and I'm going to aggregate each column by applying numpy.mean to it. So it's actually the same exact thing as the line above. So it takes each column and applies np.mean. So why learn ag when we have the very simple basic function here? Well, because we can apply any function we want, including 2 at a time. So here, I'm going to group by species and aggregate for each column numpy.min and numpy.max. So what we are looking at is for each species, for each column, the min and the max. So for setosa, the min sepal length is 4.3, the max sepal length is 5.8. Interesting. Now, do you guys think, given the mins and maxes of each column, can you come up with right now a good distinction between any of the flowers? Why? How?
The max of petal length is lower than any of the other mixes.
Look at the max of setosa and the min of versicolor. There's 1.1 centimeters in between. It seems like if petal length is less than 2, it almost seems safe enough to just call it a setosa. Anything else? How about between versicolor and virginica? There doesn't seem to be any clear-cut. Let me make this a little bit like this. Oop, no. Oh. Thanks, data frame. You're the best. So petal width, 0.1 to 0.6, the max, and then 1 to 1.8, and then 1.4 to 2.5. Can you guys give me, it doesn't seem like there's any clear-cut distinction, like a very easy number to cut off. But could you give me an estimate? Perhaps. Like, if petal length is less than 2, call it a setosa. Fine. But what about between versicolor and virginica?
Maybe between 3 and 4.5.
What, petal length?
Yeah.
Okay. If petal length, so if it's less than 2, setosa. If, so if it's not this, if petal length is, and again, what do you want?
If petal length is between 3 and 4.5.
So if petal length is between 3 and 4.5, call it a versicolor. Correct? that what you said? And then else, it's Virginica. That's the only other option. Basic human learning. Here I describe ag. We can use, and we'll use that in a second. There is a function, we went from NumPy to DataFrame. To go from DataFrame to NumPy, we call it dot values. So if we sort by sepal length dot values, it will give us a n-dimensional array in NumPy. So this is how you go from DataFrame to NumPy using dot values. Similarly, sort by sepal width dot values, sort by petal length dot values, sort by petal width dot values. So using what we just did, the next thing I'm going to ask you to do is let's skip 105. Well, yeah, let's skip 105 for a second. But I want you to create, iris dot feature names. Right. Features. Got it. Okay. Notice the order: sepal length, sepal width, petal length, petal width. What I'm going to ask you to do is not 105. I'll save that. You can look at the answer later and do it on your own, but I want to save some time. Let's go directly and do classify iris. So in the next 5 minutes, talk to your partner. Figure out a way to take in data will be a list of 4 numbers. What are those 4 numbers? The first one should be sepal length. The second one should be sepal width. The third one should be petal length. And the fourth one should be petal width. This function will return I have no clue always. When you're done, or you think you're done, run these last 2 lines of code and out will pop an accuracy. So because I guess I have no clue all the time, I was 0% correct. I was right 0% of the time. So make this a function that takes in a data of 4 numbers and outputs either Setosa, Versicolor, or Virginica. And when you're done, just run the last 2 lines and it will automatically spit out the accuracy of your function. And feel free to use this. Up here. See if you can figure out how to do this. Remember, petal length is the 3rd element in the list with index 2. So data 2 would be your petal length. So take the next 3 to 5 minutes and create a function and compute your accuracy.
I was just taking a break.
You're taking a break? This is a break. This is need a sleep. You good? All right, we have a little less than 2/3 accuracy on the table. Who can beat it?
I use that
0.85. We have 0.85% accuracy on the table. Who can beat it? 0.89 on the table. Point 0.91? I got 0.3 so far. Point 0.37. .96 on the table. Sorry. 0.96 on the table. Who can beat it? You can beat it. I think people will beat me. So as your model gets more and more sophisticated, your accuracy, your metrics will improve. Now, accuracy is one of about 5 metrics that matter in classification, but generally people regard it as a baseline metric. So when I have a 96% accuracy, what that means is, of the 150 flowers of me predicting, I got 96% of them correct. Now, I'll encourage you to play with this on your own. Try to get better than I did. This is what the answer to the pre-work and then the solutions. So, see, and I have students have beaten me, and to beat me, you can add more elifs. So you can make more rules. It doesn't have to be just 3. If it's this, it tells if it's that, Virginia, if it's else, versicolor. You can add more ifs, and that's how they did it. You can add more ifs to get more specific. If petal length is in this range and sepal width is in this range, it's a versicolor. But if it's in this range, it's a virginica. You just keep adding very specific rules. But that is fun, and I will encourage you to do it on your own time. Because what I want us to turn to now is O5KNN.py. This part does not have solutions that you can look at very easily. And what we're going to do for the rest of the time is this. This is what I'd like you guys to work on for the remaining 35 minutes. Now, what this all is an implementation of KNN from scratch, from the ground up. And I'm going to go through the code base in a couple of minutes, and I'm going to let you guys loose to go through it on your own with your partner to fill in all the blanks. So I made some imports. Part 1. The first thing I ask you to do is I give you a function that does Euclidean distance using NumPy. So if given 2 NumPy arrays, it will return the Euclidean distance between them. The distance formula. I'm giving you that. So if I do Euclidean distance of 1 and 2 and 3 and 4, and there are NumPy arrays. NumPy array. Stop doing that. NumPy array. It will give me the distance between the point 1, 2. So 1, 2, and 3, 4. The distance is 2.83. So I'm giving you Euclidean distance. So the first thing we'll do is we'll read in that iris CSV that I made last time and you just watched me recreate from scratch. So we have this iris data with iris setosa, iris virginica, and iris versicolor. The first question is to actually take the data and turn it into a NumPy array, a 2-dimensional array. It should look something like this. I'm not going to tell you how. You've seen it today, earlier in the code. I'm not going to tell you how. The next part is making a prediction. So here's our unknown, and here's our K. And I give you the steps on how to do a KNN analysis. Make a list distances, where the distances is the first element is the distance, and the second element is, let me start over. Distances will be a list of 150 elements. Each element will have two different data, 150 objects, each object is a tuple. In the tuple, there's two elements. The first element of that tuple is the distance from unknown to that point, and the second is the species of that point. So, more visually, the first row of iris is, we have sepal length of 5.1, 5.1, 3.5, 1.4, and 0.2. That's the first row of our training set of our supervised model. Our unknown, right here, 6.3, 3.1, 5.1, 2.4. Six point three, 3.1, 5.1, 2.4. When I do the Euclidean distance between 6.3, 3.1, 5.1, 2.4, and the first row of the data, 5.1, 3.5, 1.4, 0.2. What? Oh, and then you do the right syntax by putting the square brackets in here. And you go, no, and you go here. I get 4.486, which is exactly the distance of the first element of distances. So distances is the distance to each of the 150 flowers, and the second element is the flower. I wrote setosa, but you can do iris setosa, iris virginica, iris versicolor. It doesn't matter as long as they're separate and you can tell which flower is which. Does that make sense? What distances is supposed to be?
Yes.
Okay, sorry for doing that. Nearest is just the three of the distances with the smallest distance. Those are the nearest ones. So in this case, K, use K. It would be K of the nearest neighbors. And then, of those three, we're going to find the most common flower. To do so, we'll use a module called collections, which is a very simple way to find the most common element in a list. If you import collections, counter, here's a sample list where the most frequent element is 2. So you can use the counter method to do counter of the list dot most common 1 0 0, and that will give you the element that occurs the most frequently. And the idea is, if you give me 3 flower names, setosa, setosa, virginica, if you run that into the counter formula, it will spit back just setosa. So to go through all that, you have a single unknown flower here. I've defined K, 3. The first thing you do is create the distances between that unknown to each of the other flowers. Then you grab the K nearest ones with the smallest distances. You find the most common flower in that list of K, and then that is your prediction. That is KNN. Do that, because the next thing we'll do is we'll just put all of that in a function, and then we'll run that function on the entire data set. There's nothing to fill in here. This just gives you accuracy. So that's what I want you to work on for the next 25 minutes. Those parts where I ask you to fill in. And we'll come around and answer any questions. If you have any questions or clarifications, please let me know.
It makes sense.
Okay.
I just,
That's my sheet here. Where are you lost?
No.
Or just
Yeah.
Well, I just-
Are we doing class? Us here. Try the first one.
So you're gonna say like 0, 0, 0. But you're so that's
Camera's out.
he's giving you 1 that's great. That's what you know.
Oh, I'm just going to see.
Yeah, once you have the business, you want to find the BNS soft systems that they
For the first one, 35, the fill in to make the NumPy array, you could use iris.data. However, what iris.data leaves out is the species. So you need those 5 columns. Why do you have those 5 columns? There's a one-line way to go from this data frame into a NumPy dimensional array. It's a V word.
I was looking at the stock values thing here, before and it's not tracked. Oh, I didn't understand what I was supposed to do. Yeah. Like, you had to, like, put something here that makes sense. There's like,
So you don't be just So what am I thinking?
That is like completely.
Which is completely.
Okay.
Sorry. I feel like my
I'll tell you right now. Does someone want to tell me their answer for the first one, the line 35? How do you take that data frame we just made and turn it into a NumPy array? Like this? You don't even need that. That's it. Iris data.values. That's it. Iris data.values will take in a data frame and just return a NumPy array. That's all you need. Nope, you don't need to do a NumPy.array. You can do it and it won't change anything, but you don't need it. Dataframe.values will spit back a NumPy n-dimensional array. That is the answer for the first one. Move on. Keep going.
Yeah. So you got to do much loss trying to average on the salary of each candidate, not
There's a YouTube channel. There's also a YouTube playlist that has all of our. So you watch 66 hours of fun. That's a look of knowledge.
I always say I asked one question about what I should be looking through. That we can go through on the or how would we go through?
Well, so what do you want to do?
Each of them.
Yeah.
Even though I guess
Each one. No. So what are you looking for? This. This. And for each of these rows, we choose the first four. Include this in the first four. And then column.
But then there's the part after that we have to this is just a very basic function. Where this is basically comparing the actual, we're passing in two different data sets. Now, there's four of us. Not sure.
Oh, that's right, yeah. Okay, so you see what you're
Very close to that.
So, can you tell me what's going on?
Unknown is a question. That was like flower. Nearest thing. Just imagine something.
Take exactly two arguments.
There's 150 of these flowers, now there's 100 here.
So, how do I, okay, so the graph data. Oh, no, I was like, where's my number zero? How do you use species? So you get
Well, what you're going to do is for each of these rows, right? For each row, you're going to look at the first element. And take the Euclidean distance.
Oh,
These numbers.
oh, and then we're giving the name. The name.
Yeah, here's the name, so this is the column name. That's distances. Did you hear that, Fred? Does that make sense at least? Theoretically? Okay. Try doing it in code. She'll help you. Right?
Yeah.
So for distances, I'll show you how I would do it. Here's how I would do distances. For each row in Iris data, my list comprehension, for each row, I'm going to take the Euclidean distance between unknown and row except for the last column, because the last column is not a number. Euclidean distance between unknown and the row, and then also with the species of the flower. And then that will give me, why didn't it work? Oh, because I forgot a parenthesis. Oh, distance. What are you talking about? Hold on. Don't look at the man behind the curtain. Okay. And I will actually leave this so you can read it up here. So I made for each row in Iris data, I made a tuple. The first element is Euclidean distance of unknown and row without the last element being the flower species. Second element of the tuple was the last element of the row. And then I did that for each row in Iris data. Yeah, so if you want to do it without a list comprehension, what you could also do is initialize an empty array, distances equals blank, and for each row, for row in Iris data, what you can do is you can say the flower data is the row without the last column. I'm going to append to distances, or I'll even make it, I'll break it out even more. The distance will be the Euclidean distance between unknown and the flower data. And I will append to the list tuple of distance and the last element of the data. So here I've done the same thing, and I studied math, not spelling. Here I made the array in the exact same way, exact same array without a with comprehension. And these answers, as always, will go up on the GitHub. Whoa. Here it is a little bit bigger. Sorry?
The 1771 is also it doesn't know.
Is the what setting again?
So those two, the first one,
Equivalent, completely equivalent.
That's everything.
Nothing. Oh, the slash allows me to write code on the next line and still be valid. So there's actually nothing after the slash, it's below it. See? Nothing after this. It's just so you can see it a little easier in bigger font.
Define the access.
Now we want to reform iris data to it's giving us the whole row. Yeah, so this is a 3D. Okay. And that's why when we think we're pulling off, like we're it's saying here's this whole thing, and then you would see function. Okay. So we want to do iris data. What is iris data? 0, and then it's
So we're just going to call that function.
Are you still having shape problem?
Yeah, it's a shape. So iris data is 3-dimensional.
So we need to yeah, 0. I just put it
Oh, if you put the numpy array around it creates the third.
Yes.
That creates the third.
So this is iris is
Values. So now we used it. Before. You put the numpy array around it, you create a third dimension.
Well, you already did it. I just asked you like because you have 0, 1, 2, 3. Well, we're gonna do the top of this. So I'll let you. You good?
Yeah, I think so.
Okay. So we don't have to. Now I know.
Yeah, because it's not a single element. So putting it in that as 0.
So you want to sort these by the equivalent distance? So I would also put it yeah, so we can take that.
For the nearest one, any thoughts? We have distances. How do we get the 3 of them with the smallest distance? Someone raise your hand, tell me. How would you sort it? Sort index, it's not a data frame. Watch this. A NumPy array can be sorted. Like with the normal sorted. And it does it by the first element. Look at that. It does it by the first element. So when you sort it, how do we get the k nearest neighbors? We take the first, I'll call it k, so we can change k. We take the first k values. And then there they are. Those are the 3 flowers closest to the data that I gave you. Oops.
So it's a sort of,
You can do a sorted list or a NumPy array, but it won't do a data frame. Yeah. So once you have nearest, finding the most frequent flower should be pretty simple, because all you have to do is of each of the nearest, take the second element. So this column, quote unquote, which is the most frequently occurring flower, it's going to be Virginica. So your prediction, final thing, will be, I'll take this counter notation, but the list I want is for each nearest, the second element. And then I'll do which means my prediction is Iris virginica. So here I just copy and pasted the counter notation from right here and replaced the list with the second value of each element of nearest, because nearest is a tuple of distance and species. So I took all of the species and I just found the most commonly occurring one. So take a second to look at the syntax, understand it, and the last 5 minutes I want to show you something.
Could you save it to your...
Yeah, I'll put it on GitHub. Yeah, all this will be on GitHub, and it's also, if you watch the video, it's all in the video as well. So take a second to look at the syntax. It will be on GitHub later, of course, as always. But take a second right now and look at it, because I want to show you something. It's going to blow your mind. This one? This one? Okay. I took the counter notation, which takes in a list and spits back the most frequent element. I copy and pasted it. And instead of L, I gave it another list. The list was the flowers in nearest. N1 for N in nearest is the second element of each of these, which is the flowers. So when I take this, it's Iris virginica, Iris virginica, Iris virginica. The most commonly occurring element is Iris virginica. So in KNN, we found the distance between the unknown value in each of the rows. We took the 3 with the K with the smallest distances, and of those K, we found the most commonly occurring flower and said that's our prediction. Now the last part, what we're going to do is we're going to take what we just did, and I'm going to copy and paste it into this function. What this function will do, I called it predict. It will take in an unknown value, and it will spit in a k value, which will default to 3, and it will return the prediction. So I'm literally taking all of the code I just wrote and throwing it into this function. Nearest, and then it will return the counter like so. All copy and pasted. So that, oops, that's the Virginica. So that when I run, I now have this function called predict. Predict will take in a set of values and it will just spit back its prediction. So these 3 lines of code were the exact literal copy and pasted lines of code that I just wrote above and just put them in the function with an indent. So now this function can be called on any row. So what we're going to do now is here is going to predict each row and give me an accuracy. So using the KNN we just built, it gives us 0.959 accuracy, which is, if you remember, the same accuracy that I got using the human learning technique with the petal length is in this range. So that's not very Good, if I can do it by myself without the machine. Well, here I'll do it with k equals 5. When I run it with k equals 5, I get 0.967. Goes up. Here I'll do it with k equals 2. Only 2 neighbors. And when I do that, I get 0.979. My accuracy is going up. And I will leave you with one thought. What if I only use one? One neighbor. That should be pretty bad, right? Because I'm only looking at one thing, right? Why does that give me 100% accuracy? I will leave you with that question until Wednesday when we answer it. How did 5 neighbors give us an accuracy of 97%, but only looking at the one nearest neighbor gave us 100%? How does that make sense? Which is why model evaluation metrics are really, really important, because that shouldn't make sense. So the homework is to complete the pandas work that is assigned for tomorrow, or for Wednesday, as well as the project milestone, so you've known about that. Down at the bottom, I've included a reading. It's just an article that I want you to read called Understand the Bias Variance Trade-Off. It's a very well written, a lot of pictures, a lot of explanation about what is bias versus variance. And there's an interactive demo as well, which is really nice. You can move the number of nearest neighbors and it shows you how things change. Whoa. A couple of questions to think about. We're going to be discussing it on Wednesday. For a more in-depth look of what we just did with machine learning, I've included a link to a free PDF called the ISL, the Introduction to Statistical Learning. Section 2.1 is their Introduction to Machine Learning. It's about 14 pages long if you want to get a much more in-depth look at machine learning. But other than that, you know your homework, project, pandas. Congratulations on building your first KNN algorithm. I will be posting the code to what I just did on GitHub. Wednesday, we will look into scikit-learn. Scikit-learn is the built-in Python module. Pandas is to exploratory data analysis and visualization, as scikit-learn is to machine learning. It is the go-to thing we will learn to use machine learning. It will do KNN in 3 lines of code. It will do most of our machine learning models in about 5 to 10 lines of code. So it's going to be our go-to pre-built machine learning library. And with that, I bid you all good night, and I will see you on Wednesday.